Hi. So today we will be discussing how an online whiteboard system like Excalidraw or Figma collaborations work. We'll be discussing the architecture of something known as CRDT and how it comes to the rescue. This walkthrough is going to be very incremental and we will be discussing steps one by one in order to know that what breaks and what we can do incrementally to fix a problem. So first of all, let us discuss making concurrent edits to a single shape. So for example, let's assume that we have a rectangle on our canvas and Alice is trying to move it to x is equal to 100 and Bob is trying to move it to x is equal to 300. Both use their wall clocks to apply the principle of last right wins. The Alice's wall clock says this time and the Bob's timestamp is this. Clearly, Alice has the wall clock of a later timestamp, so Alice's stroke should win. So we keep the stroke of Alice and we lose Bob's stroke. But in reality, Bob made the later stroke, but Bob's clock had drifted, which concludes that wall clock isn't the truth always. In distributed systems, we always say that clocks always lie. So we cannot trust a wall clock. Here, Bob, who made a later stroke, lost but shouldn't have lost. So, what do we do here? First of all, let's discuss what was wrong with the central server and this model of last right win. First of all, there's too much of latency because of this central server. Every stroke has to sync with the server before getting applied locally as well as to the other clients. Second, wall clock lied. In most of the cases, wall clocks will lie. Third, if a client is offline, they are clobbered. That means they stay behind and they cannot sync later on. And the central server is the single point of failure, which becomes a bottleneck in our system. So, how should we fix it? We should just drop the wall clock and we should use a logical clock. Now, how do we use a logical clock? A logical clock is nothing but just one counter per client. So, for example, we are at count 0 and then we make a stroke. So, for example, for Alice, if she makes her first stroke, the counter will increment to 1 and her logical clock reading will be 1A. Then she sends it over to Alice. Now, sorry, Alice sends it over to Bob, the stroke. Now Bob, who has the counter 0, receives 1A and makes his own edit. Now we will pick the maximum out of 1 and 0, which is current stroke of Bob, and we will increment the maximum by 1. So it will be 2B. We'll ignore what is written on the board for now. So it will be 2B. So this is the formula which is used. So we pick the maximum of hours and received and we increment it by 1. It is known as lamport clock. And similarly, if the 1 comes over here and Alice is at 1, so 1 maximum is 1, we increment 1 by 1, so it becomes 2, so 2A. So that is how the logical clock reading is calculated. So we saw how the higher counter wins. So it is very deterministic, but we need the correct data type for merging the strokes in the concurrent shape, in the same shape. So we choose something known as a CRDT. CRDT stands for conflict free replicated data type. Here, each replica updates independently and then we merge it using some rules of this data type. There are two types of CRDTs which we will compare in this use case. First is state-based CRDT. Here, we send the whole state A and B and merge hours and incoming state. This is very robust to duplication of messages and this does not lose any messages, very delivery friendly. But as the states can be large, it is bandwidth heavy. Whereas on the other side, operation based CRDT just sends the operations one by one. So the payloads are obviously tiny, but it needs an accurate delivery protocol. For our use case for collaborative canvas, we used orb based CRDTs because the edits are small and fast, and snapshots which we will make for the joins will be made from this operations. Now, why this CRDT is conflict free? So a merge is a join. That means it converges to the same state. So a merge must satisfy three laws in a CRDT. First is the commutative law. If we merge hours and incoming state, or the incoming and hour state, the result should be the same. The order of merging should not matter. Now, associative. If there are three clients, we merge the first two clients together and we get a result, and then we merge that result with the third client, this thing, and we merge the second and third client together and then merge the result with the first client, this result, these both must be same. The grouping should not matter. And idempotent, that is, merging the same state with itself must produce the same state. So it deduplicates the merging of the same state with itself. So that's why we say that a state forms a semi-lattice and a merge is the least upper bound. That is a join. That means it converges to the same state. So the canvas which started empty diverges to two different states, which on merging converge to the same state. Now CRDT runs on every client. Now let's see how CRDT is operated on every client. Every CRDT has the state, that is the canvas state or the document state. There is a local operation log. It helps us with offline syncing. There is own counter plus client ID, which is used for the lamport clock, and there is a version vector. This version vector helps us to send only the required payload across. We will see it in detail later. Now, how the loop runs. First, the user applies the edits locally, and these apply instantly without sending anything over the network. Then we generate the lamport clock by incrementing the counter and attaching the user or the client ID to it. Then we append it to the log and we broadcast it. Then the other client receives the log, or our client receives other client's log, and then we merge the states using the CRDT principles. So this loop continues infinitely or till when the session lasts. Now we discussed what happens when there are concurrent edits in a shape. Now, what happens for how do we keep the record of all the strokes which are ever generated, or all the shapes in the canvas, or all the chat history, whatever is going on in the canvas? We use a grow only set. So, what happens? Alice draws stroke 1A, stroke 2A, Bob draws stroke 1B and stroke 2B. Now these both are merged. This is a grow only set. That means it only ever grows. That is the union of these two sets. Now this satisfies all the three laws of CRDT, which is it is commutative because A union B is equal to B union A. It is associative as well, and it is idempotent because A union A is A. Now this will always merge. This is the canonical CRDT. G set, that is grow only set, is a CRDT. Now, how do we delete from a grow only set? Because if we try to delete from a set, if Alice deletes 3A, But Bob doesn't know that Alice deleted 3A and it is still there in Bob's set. So if we union Alice's set with Bob's set, we will see 3A back in the union. So we use OR set, that is observed removal set. Now observed removal just uses the concept of tombstones, that is it tags the stroke with the deleted footnote. So w- we use a different grow only set for tombstones, that is the deleted strokes. So Alice drew 3A, so it goes into adds. Alice removed 3A, it goes into this G only set, 3A. Now when we render this on the canvas, we just remove these things in the tombstones from the adds union. So I think it makes sense. So these both are completely different from how we do concurrent edits on a shape. Their last right when rule is applied, and this G set and tombstone principle is only used for maintaining a record for all the strokes which are ever made on the canvas. Now we will discuss what is LWW-Register, which is last win right. Now there can be two types of things, that is competing over the same property, or there are two different properties which are applied concurrently. Okay, makes sense. So here Alice changes the color of the shape and Bob just moves the coordinate. So as these are two different properties, we won't look much and we will just merge them without any contest. But if there is the same property concurrently, we will use the Lamport clock and we will make the one with the highest counter win. So this makes sense. Now let's go over how we sync both the operations, that is the operations coming from both the clients using something known as version vectors and deltas. So if birth change, we resend the whole document, our bandwidth will be fucked. So what we use is that we track the highest counter seen per client. So for example, there are three clients, Alice, Bob, and Carol, and Alice has 9 strokes of Alice herself, 6 strokes of Bob, and 4 strokes of Carol. And Bob has only 7 strokes of Alice, 6 of Bob, and 4 of Carol. So Bob and Alice agree on Bob's and Carol's stroke, but Bob is 2 strokes behind from Alice's stroke. So from Alice's CRDT, only 2 strokes will be sent to Bob, that is stroke number 8 and stroke number 9. This ensures tiny payloads and the offline catch up is clean. So, for example, if Alice is ever offline and she comes back online and she is still synced with 6 strokes of Bob and 4 strokes of Carol, she only needs to send the 2 strokes of herself, which everyone else missed when she drew while she was offline. So, hope this makes sense. Now, what kind of topology should we choose for such a whiteboard application? First of all, is a central relay where there is a server and all clients are connected to the server. So here the authentication is easy and presence will be easily detected and there is ensured durability. But server being central gives us a single point of failure, whereas there's something known as peer-to-peer or mesh where every client is connected to each other. Here we can have a true local first architecture and there is no central node, so there is no single point of failure. But the discovery of every pair is difficult. We will have to do something like network address translation and the authentication is very difficult. What we will pick here is central relay, but we will make the architecture fan out from server to every client. Let's see how we will achieve this. So first of all, we have our CRDT clients, which have their own op logs and their own CRDT replica. And we will have a WebSocket gateway, which will be the relay between this client, but it is not the central brain. It just fans out the strokes from one client to the remaining n minus one clients, and this gateway can be sharded by board id. That means every board will have a single WebSocket gateway. Now, apart from relaying these strokes to the remaining client, it also appends these strokes at the server, which has the op log, the snapshot, and garbage collector for the tombstones, because we don't want to accumulate the tombstones every time. We want to remove the tombstones regularly so that our storage does not fill up with redundant tombstones, and then we will have an object store. So yeah, this is how our architecture will look like. We'll come to the recap and this thing later, but first let's see how our whole machine works. Let me zoom it out. All right. So first of all, our clients will sit here, which are three clients: Alice, Bob, and Carol. Alice draws a stroke which renders instantly on her canvas, and it is given a Lamport ID 12A and appended to the local log so that it can sync if Alice is offline, and then it is broadcasted. So Alice sends this and it is sent to Bob, but it is not sent to Carol because Carol is offline. Now Bob changes the color 13B and it is sent to Alice. And these two have no competition because these are two different operations as we saw above. Now Carol, who is offline, his stroke will be synced later on. And we see that as he makes a stroke 9C, which was behind the current stroke, which was made by Bob 15B, Carol loses and Bob's stroke wins. And there is a WebSocket gateway, which we discussed, an op log, a snapshot mechanism, which truncates the old and redundant op logs by maintaining a state of what the current canvas looks like. And then there is an object storage. And we saw what is the happy path, and we saw what is the sad path. Now, this is the pictorial representation of what we just saw, that Alice draws first, Bob recolors it, there's no contest. Carol, who was offline, drew something like this, but Bob had a newer version, so when Carol comes online, his stroke loses against Bob's stroke, which is more recent. Now, let's go over to these things. So, what we saw, let me zoom it in. Yeah. What we saw first is that logical clocks are the answer over the wall clock. Then we saw what are CRDTs, what is the client loop, G set, OR set, and LWW sets and their use cases, and how version vectors are used, how we use snapshots in very brief. And the central relay is actually a WebSocket fan out. All right. We have simplified many things such as L last right win drops the loser. So we should never drop them. We should always keep them somewhere stored. And concurrent delete plus edit needs an explicit rule that if we are editing something, what should win? Delete should win or edit should win. So usually delete wins. Now we discussed about this. Tombstone garbage collection isn't free. It depends on the version vectors. So when do we have to garbage collect? So prune a tombstone once every replica has seen the delete. So once every replica acknowledges that, okay, I have seen that this stroke is deleted, then we garbage collect it. And then what is a mega board, what is spatial sharding, trust, server, images, storing blobs. These are out of scope for this video, but these are worth wondering and tinkering about. So yeah, so this is how the system design of this thing works. There can be many things which can be added over it. But I guess this is it for the video. I hope I made sense for most of the video. And if I did not, I'll try to bring it in a better way the next time. Thanks a lot for staying through. Bye.